Okay, guys, if you look at this question here is a fact. What? Oh. Thank God someone mentioned that the screen is not on after 5 minutes of talking. Thank Jesus she's here. If not, I'll be talking to only the online students. Very good. Hey, Melvin, welcome back. Good afternoon. Disappeared. Okay. Hurry up, sit down. I want to start class. Okay, everyone, if you look at this question here, it's a very simple one, right? Basically, they said in figure 10.1 shows the gap between N pole and the S pole, the magnetic field is uniform, right? On figure 10.1, draw they specified 4 lines to show the pattern of the magnetic field and the direction of the magnetic field in the gap, right? So if they only ask you to draw 4, you just draw 4. Now the trick here is you could either draw like one curve one here, another curve one here, and then like 2 in between, which would ideally be equal distance apart, right? It would ideally be equal distance apart. This is 1, right? Or you could have just straight away drawn the straight lines, right? But if you have drawn the straight line one, like for example, this one here, right? I only want to say is that number 1, make sure your arrows are 阴面有没有做好功课？ The only thing is, number 1 is make sure your arrow is going from north to south, and number 2 is, like, I can't draw this on this screen right now, but make sure that each and every one of these distance are at least from the eye level the same, yeah, guys. If they are not equal distance apart, you are wrong, because they already specified that it is a uniform magnetic field, guys. Right, so this is definitely one of them, and it's 2 marks. Easy. Okay. Yeah, make sure that your gap here is the same. Don't like one gap big, one gap small. It is not going to be acceptable, especially if they mention that it is uniform magnetic field. Okay. All right. Then after that, the next part here, figure 10.2 shows a horizontal copper wire PQ between 2 opposite magnetic poles. The circuit is made by connecting a sensitive digital ammeter between P and Q. Hey guys, when you see this word sensitive digital ammeter, sensitive means to say that it can measure very small changes. Like for example, sensitive means to say it can measure up to 0.1 ampere, or if it's even more sensitive, it will measure even more small, like 0.01. So when you see the word sensitive, means to say it can measure very small. While PQ is moved vertically downwards. Oh, PQ is moved vertically downwards. State and explain what is observed by the ammeter, on the ammeter. So first and foremost, we state what's gonna happen on ammeter. What do you think is gonna happen on ammeter? It will sorry, the ammeter will not generate current. The current is the one that causes the ammeter to what? To what? Wait. You're supposed to mention the ammeter deflects, right? It is due to the fact that there is current flowing, right? So your statement is number 1. Because you see how they ask you to state and observe what is happening on the ammeter, right? So obviously, as soon as I swing the wire through the magnetic field lines, it's cutting through the magnetic field, and thus electromagnetic induction occurs. So your first statement is that the ammeter deflects. This is your statement. Right. Then after that, you need to go for your explanation, ma. Why is the ammeter deflecting? And it's worth 2 marks, Why? Good. The conductor is cutting through the magnetic field and then generates what first? No, before current, there's something that comes first. What is it? Starts with the letter E. Oi, Sang Ming, oi. 没有做功课, bloody hell. What does it generate first? I keep telling you guys this, something must come before the current. What is it? Before the current is generated. And it starts with the letter E, boys and girls. What is it? Oi, EMF, bro. What does EMF stand for? What does EMF stand for? Wow. Electromagnetic force. Right. So you're supposed to explain as the conductor, the copper wire cut through. The key word here is definitely cutting through the magnetic field. All right, cut through the magnetic field. Electromagnetic induction occurs, ma. Guys, every time you talk about all these kind of electromagnetic induction, you must always mention that the EMF is generated first. It is because of this EMF which drives the current in the circuit, guys. Very, very important. You must know how to answer this because it 最大的，再大就看不到了，是不是我的字有一点错？你看不到吗？真的这样子？Is it better this way? But anyways, ammeter deflects as the copper wire cuts through the magnetic field. Electromagnetic induction occurs. EMF is generated, which induces the current. 可以吗？ Oh, this is a very important question, guys. You must know this. As you can see, I think every question that I've included in the past year paper also has this question. Okay. Then after that, the next part here, state what is observed on the ammeter when PQ is moved vertically downwards at a greater speed. What's going to happen to the ammeter if I move it down with a greater speed? Good. The ammeter deflects more, right? The ammeter deflects more because there's obviously more current now, right? What about if I vertically upwards at the same speed as 1? What's going to happen? If I move it vertically upwards, because now it's down, now it's up, what's going to happen? Decrease? What? Why will it decrease, guys? It's not going to decrease, by the way. What's the real answer? Eugene, what's the answer here? If I move it vertically upwards instead of downwards, what's going to happen to the ammeter? Your head. Huh? Same as the first one? Definitely not. No, it will not. That's not the right answer.
current generator.
Okay, guys, think back about the Fan-Jian rule that I told you about, guys. What happens when you move the magnet in opposite directions? What's going to happen to the current? No recollection. Oi, bloody hell. You know what I'm talking about, right? Do you know or not? Whoa. What's this? What were we talking about here? Why, when we move in the opposite direction, what's going to happen? What happens here? What's going to change? Good. The direction of the current changes. Why? Because Lenz's law states that the induced current always opposes the motion producing it, right? It will always oppose the motion producing it, If I go in, initially here was north and here is south, the ammeter is going to deflect in this direction. But as I'm pulling it out, what's going to happen is this will be north and this will be south. And because of that, the ammeter will deflect in the opposite direction, right? So this question here is actually testing your understanding on this part here. You're supposed to state that if the wire is cut down, the ammeter will deflect in one direction. But if the wire is cutting upwards instead, the ammeter will deflect in the opposite direction. You understand what I'm talking about, boys and girls? That is your answer here. The ammeter will deflect in the opposite direction. Okay, everybody. Anyone's got any questions for this chapter here? Anyone wants me to remind them anything that they may have forgotten over the Chinese New Year? Anyone? Anything? Yes. 一个是找 current, right? One of it is find current. Which one is the one that you usually find current with? Left or right? It's the right. Why? Because when you see someone you don't like, you always point them the middle finger with this, right? The right hand, the dominant hand, right? Then the left hand is for you to be a sarcastic thumbs up. Always remember the angry middle finger and the sarcastic thumbs up, right? So if you're the angry middle finger, it means to say this one is to find current when you're given the, what's this again? Force and magnetic field. Remember your mother, your mother point at you, right? This one is magnetic field. You can only use right hand rule if you're given these two. If they give you current and they give you magnetic field, then you must be using the Fleming's left hand rule because most of the time you'll generate the force. You all remember now? Good. Next question. Anyone? Has anything they want to talk about? Okay, if no questions, then we move on. Okay. Now, today we're going to learn a new thing here. This is essentially what we call a AC generator. Who here has no idea what an AC generator is? Do you all know what an AC generator is?
Air condition generator. Air
Sorry,
condition. Air condition.
Air conditioner. Yeah, you could say. No, we're not. Actually, no. Your air condition will not have an AC generator there. It's not. It's not air conditioning. AC means to say alternating current generator. Guys, can you give me an example of when will there be an AC generator? Guys, if you think about it, the word here AC generator, AC means to say alternating current and generator is means to say to generate, right? In other words, this thing here actually supplies electricity on you, and to be more exact, it supplies the alternating current that comes from the wall sockets here. So where do you think will have the biggest AC generator in Malaysia? Which company do you think owns the biggest AC generator in Malaysia? 啊？对 ，yes，发电的地方就是 in Malaysia TNB 啦 ，right? Because TNB has to generate the huge amount of electricity that is consumed by Malaysians every day, ma. So how does a AC generator work? Today, if you want to know how an AC generator works, we go back into the chapter of energy. If you remember, I talked about generators before in energy, because initially, okay, so a very simplified version of a generator will look something like this. Okay, the bottom part here is where they put the fuel, fossil fuel, coal, or even nuclear fuel. Okay, so it could be fuel, it could be coal, it could be even nuclear. Okay, this nuclear only has one purpose only, to be burned. Okay, and when we burn this, right, what happens is obviously it will generate a very big fire. This very big fire will in turn be used to do what again? You all remember? I see the confusion in everyone's face. It's used to boil water, guys. And when they boil this water, right, it will actually generate very, very high power steam. Okay, it will be very, very high power steam. Okay, this very, very high power steam is used to spin a turbine, a very ugly looking turbine. The real turbine doesn't look like this, but it's just for you to get the idea. This turbine, right, will spin, right, which is connected to a shaft. Okay, a shaft is just a fancy term to say a very big stick. Okay, a very big stick. This shaft will be connected to a power generator. Okay, inside this power generator, it will actually convert kinetic energy into electrical energy. But here is the question: how do we convert kinetic energy into electrical energy? How does this power generator actually work? If you think about inside this power generator, it is essentially, you know how we learned about electromagnetic induction 2 weeks ago, right? We said that when there is a magnet, right, and then there is like a conductor that swipes down or up of this thing here, it will generate electricity, right? This power generator is basically this inside, but a much more sophisticated version. How will it look like? Let me show you right now. Yeah, I need to show you how a power generator works first. Okay, this is a good one. You see this thing here is the power generator that I was talking about. And then this one here doesn't use a turbine, it uses a belt instead, which is just something spinning it. Then you can see that the current keeps flipping left, right, left, right, left, right. It flips left, right, left, right, left, right, because it's generating alternating current, positive, then negative, then positive, then negative, then positive, then negative, then positive, then negative.
Current that keeps reversing its direction of flow. An armature, consisting of coils of wire wrapped around an iron core, is rotated in a static magnetic field.
This one here is basically the inside of a power generator. But instead, in a real one, they won't just have one coil. They're just showing you one coil right now because they want you to understand what is going on. Inside, you see these red color things here? These are the magnets. This yellow color thing here, this is the coil that is continuously spinning and cutting through the magnetic field, which in other words is continuously generating electricity.
Field. The movement of the coil through the field causes an electric current to flow in the wires. When wires in the coil cut through the magnetic field between the poles of the magnet, current is induced in the wire. When the coil is turning in the direction shown, current flows toward the right in the far side of the coil and toward the left in the near side. The current flows through the wire in one direction during 1/2 of the turn. As it does so, the current changes from 0 to...
If you are wondering what they're talking about in terms of the current here, this is one of the Fleming's rules. Which hand should this one be? Left or right? Fleming's left hand rule or Fleming's right hand rule here? In order to know that, I think about what is being provided. What is being provided and what you want to generate in this scenario here. What is being provided? Definitely the magnetic field. Right, they will give you north and south already. So do they provide movement or do they provide current in this scenario that generates either movement or current? Which one? They provide current or they generate current? They generate current. So Fleming's left hand or right hand? Oh. You got it right already. It is definitely generating current. So left hand or right hand? Yes, it is the right hand. Right. So if you think about it in this scenario here, the magnetic field, right, will be north to south. Let's say we look on this wire here. Oh God. Can anyone see it? Okay. So we look on this wire here right now, guys. This wire here. Basically, Fleming's left hand rule point towards the right. And then in this scenario here, it is spinning this way. Oh, it is spinning this way. Oh, means to say it's coming up here. Wait, why is this current in this direction?
To maximum flow, then back to 0. During the other half of the turn, the current flows in the opposite direction.
Oh, this is the all correct one. Yeah, this is the one that spins here. And current force upwards. Wait, this thing is wrong, man. Show you the right one, which is my favorite video, this one here.
In this module, you will learn about an AC generator.
Everyone pay attention to this one. This is actually very, 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 very important. And I'll explain it part by part by part. Okay.
Generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternate.
So this diagram here right now is basically another simplified version of what it looks like inside a generator. In a real generator, right, there will be more and more and more and more terms of power. I'll explain it to you later, but right now you just understand the concept first.
EMF or alternating current.
And you'll notice the ammeter, this one here is a galvanometer. A galvanometer is basically a very, very sensitive ammeter, right? So it doesn't really matter, it will still record the same thing. You'll notice that the galvanometer keeps deflecting left and right, indicating that the current will keep going left, right, meaning say positive, negative, which is a form of alternating current.
Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD.
This is basically the coil.
It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly.
The shaft is just used for you to provide the force to spin the thing.
A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1.
This one is very important. They love, in your exam, they love to ask you what is this slip ring for. This slip ring, if you notice, guys, if you look at this diagram here, this thing here, this wire here, this copper wire here is connected like this. And then this one here is kind of connected like this. Can you guys see? Right. So it will always maintain contact with these rings. It makes sure that the copper or soft iron armature is always in contact with this ring. In your exam, when they ask you, what is this ring for? You just say that it allows the coil to be continuously spinning in one direction while maintaining connection between the rings. But I'll have it in my notes later.
And S2.
But pay attention on how this thing spins, guys.
These are connected to the armature and thus rotate with it. Two brushes B1 and B2.
These brushes are usually what we call the carbon brushes. Carbon brushes can conduct electricity because essentially right now we want the electricity to flow from here and then like this one thing to flow from here. Right, so these brushes are what we call carbon brushes.
They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result,
for those who are wondering what magnetic flux is just a fancy term to say changing magnetic field, which is what's happening here. As the coil continuously spins around the magnetic field, right, it's kind of changing magnetic field inside the copper. So whenever you see the word magnetic flux, it's just changing magnetic field.
an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current.
This is the part where you start using a Fleming's Bragg guys.
Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA.
Do you guys see that? Let's do it one by one, guys. Let's do BA first. First and foremost, your magnetic field line is supposed to point towards the right? Then because this thing here is rotating clockwise, guys, this thing here is rotating clockwise, you see that the first current here, it actually comes out in this direction, right? From B to A, right? Because it's rotating clockwise. Magnetic field force downwards and your current will be coming outwards like this, right? So you can see that the current flows here and you can check whether this is the same also. Because right now this CD is going up, right? So magnetic field line, force upwards, the current is going into the thing, so it's flowing from CD to BA, yeah?
The current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now, during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule.
So right now, you see the difference. Just now, right? Just now we know that it flow from DC to BA, right? Right now, the current will flow from AB to CD, right? You can see that just now before it spin, it was like this one. Right now, because it rotated half a turn already, right now it's flowing like this instead. That is why it will flow in two opposite directions of the current. Just now was CDBA, now it's ABCD. Right, the flow of current is different already.
Current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation.
Guys, for those who didn't catch it just now, the first cycle was here, right? Just now the current was flowing from DC, then B into A, right? Then after the 180-degree turn, after the 180-degree turns, the current right now is flowing from A, B, C, D, right? And because of this, the current will keep fluctuating left and right, because the direction of the current keeps changing.
And rule. Current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF.
Pay attention to this part. Always comes out in the exam. This one is very important.
Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily 0.
Why do they say there's no change here? Guys, if you think back on what we've learned 2 weeks ago, I said that today if I have a conductor and I keep swiping it left and right like this, will it generate any current? No, because it's not cutting any magnetic field, right? At this exact instance here, it will change. At this exact instance here, can you see that the coil is actually moving in this direction, which is actually parallel with the magnetic field? And because it is moving parallel with the magnetic field, at this instance here, it will generate the minimum amount of current, which is going to be 0. But after 90 degrees turn, you'll see that the coil will move perpendicularly against the magnetic field, which generates the maximum current. This is very important. It always comes out in the exam. Watch the graphical representation here, guys.
Hence, the induced EMF at this position is 0. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal.
You see here, at this instance, the coil is moving perpendicular against the magnetic field. And because of that, it will generate the maximum. But this will change again because it continuously spins, right? It will keep going in between minimum to maximum to minimum to maximum to minimum to maximum to minimum to maximum.
At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical, and therefore the induced EMF is 0.
Once again, at this position, at this instance here, the coil must move like this and like this, right? And because it is moving parallel with the magnetic field, it will be 0. But it will change again.
During the third quarter rotation, the induced EMF increases, but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value.
Once again, maximum because this one here is moving perpendicularly against the magnetic field. The coil is moving perpendicularly against the magnetic field and thus generates the maximum current.
During the fourth quarter rotation, the induced EMF decreases and becomes 0 momentarily at time t seconds, as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. In this
Everything is 60. So, like I mentioned, in this chapter, they'll ask a few things only. Number one, what is the coil for? Sorry, what is the ring for? They'll even ask you what ring is used in the AC generator, which you must always say slip ring. Slip ring is basically, imagine this, one ring slipping into two. Right, one ring slipping into two is known as a slip ring. They'll ask you this, what ring is this? And then they'll ask you things like, what is the slip ring for? The slip ring is to allow the coil to continuously spin in one direction while maintaining contact, right? While maintaining contact with the coil. Then after that, they'll ask you, when will it generate maximum? When will it generate minimum? And they'll ask you why. You must know that it will generate maximum when the coil is moving perpendicularly against the magnetic field, right? Then it will generate maximum. It will generate minimum when the coil is moving parallel with the magnetic field because it's not cutting any magnetic field. Understand? Okay, anyone's got any questions or not for this part here? Yes, like. Okay, very, very good question. This here is just an example of how AC generator works. In reality, there's even more magnets. Okay, so how will a real generator look like? A real generator will look something like this. If you ever open up your fan or whatever before, right, it will look kind of something like this, right? All these are magnets. All these are coils. So it'll keep spinning and keep cutting and keep spinning and keep cutting. So the maximum keeps happening more and more and more and more because it keeps cutting more and more and more. So like a real example will look something like this. Yeah, something like this. You see? Magnet, 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 coil, 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 coil. There's going to be damn a lot of coils and damn a lot of magnets on. Because in reality, the more magnets and more coils they have, the more times it generates a maximum, and thus the more times it will generate a greater current. You see something like this here. This is also one of the examples of the coils inside. It will keep spinning and spinning and spinning because it wants. In reality, an AC generator is supposed to generate more and more current, so it will keep cutting and cutting and cutting and cutting and cutting and cutting. Yeah, let me give you another example. This is the example that I talked about just now, right? It doesn't matter what kind of source it will be. It could be anything, but the idea is to generate heat, to generate high power steam, to spin the turbine that is going to spin the generator because takkan everyone is going to go there and like TNB won't hire a bunch of bunker cars and spin the thing 24/7, right? Like they're not rats, right? So what they do is they'll use natural resources, they'll burn natural resources that ultimately is to spin the turbine. Okay, and the real turbine looks something like this. Real turbine will look something like this. It will be spinning due to the high power steam. It will keep spinning and spinning and spinning and spinning. Of course, not the fan version that I drew just now. It's just like the oversimplified version, right? So it's something like this here. These are the turbines, right? Understand? Everyone have a better idea? Even this one here also is like the high power industry turbines, right? And this is the generator that will generate electricity, which has the coils and the magnets inside here. Okay, everyone? Yes, another question, right?
就是现在看到是那个就是切断那个它，然后它两个磁铁在外面，这样切断。那如果说可不可以中间一个就是对，
So in reality, it will not only have one magnet inside. Even if you want the coil outside, can, because it doesn't matter if it's the magnet cutting through the coil or the coil cutting through the magnet. Now, ultimately, the idea is you need the magnetic field. You need the magnetic field to cut through only, right? So in reality, even if you put a magnet inside, usually they'll have like maybe like 6 or 8 magnets inside, so that the coil can like every time it spins, it will cut through more magnetic field line also. You get what I mean? Yes, it is possible. Okay, very good.
Slip.
The slip ring, good. There will be notes here. Let me show you right now. Okay, so you see here. We'll ask you something like this one. Okay, let me just explain the whole thing one by one here. So this is just an oversimplified version of how the insides of a generator look like. In reality, you know, it won't just be one coil. Maybe there's another coil here, and then like there's another coil here, and then there's like another coil and coil and coil and coil and coil and coil and coil here lah, right? And then the important part here is, number one, you need to know all the parts lah. Obviously, this thing here is known as a slip ring. You must know, right? This one here is obviously the coil, and this one here is obviously the magnet field. Then this part here is important. You need to know when it will generate the maximum, when it will generate the minimum. Okay? Why is this one minimum here? Because of what? Because the coil is moving parallel with the magnetic field, and thus it will be minimum. Why is this one here maximum? Is because the coil at this instance here is moving perpendicular against the magnetic field, and then once it spins to here, once again parallel, once again perpendicular, once again parallel, and thus you can see that it will go like maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. Okay, all right. So then obviously AC generators are used to generate current through application of electromagnetic induction. Once again, the conductor is cutting through the magnetic field. It's known as electromagnetic induction. I'm inducing electricity with the help of magnetic fields. Okay, then obviously AC generators use slip rings. Like I mentioned, these slip rings are what the AC generators use. Slip rings are connected to the coil of wire. It is connected to the coil of wire here, while the carbon brushes are connected to the external circuit, right? These carbon brushes are connected to your external circuit here. Wait, the external circuit here. Carbon brushes still connect to your external circuit here. Okay, so in your exam, they'll ask you, what is the slip ring for? You say, the brushes are constantly in contact with the slip ring so that the current can flow from the coil to the external circuit and allow the coil to continuously spin in one direction. Maybe you write one more statement here. And allow the coil to continuously oh, is that how it's spelled, continuously? Oh, GG. England, no good. Continuous. Oh, that's W. Continuously spin in one direction. Shit. Good. 这把可以的呀，没有它，全部人不用看这个东西啊。Allow the coil to continuously spin in one direction. Shit, I read it somewhere. Okay, everyone. Then obviously AC generators do not generate EMF at 0 degrees because the coil is moving parallel with the magnetic field. Keyword here, as long as the coil is moving parallel with the magnetic field, it will not generate any electricity. EMF is at maximum when it's 90 degrees because it is cutting the magnetic field perpendicularly. It is cutting it perpendicularly, and obviously I can increase the EMF generated if I increase the strength of the magnet, increase the number of turns, and also increase the speed of the rotation. Exact same criteria you need for electromagnetic induction. Exactly the same. Okay. Okay, oh, by the way, guys, one more thing I want to highlight, which a lot of students they like to do. You know, like most of the questions they'll say that the magnetic field is like north and then south, left and right one. Sometimes the question could just change and say that this is the north and this is the south. If this is the north and this is the south, then you better be sure as hell know that at this instance here, because the coil is moving parallel with the magnetic field, at this instance is 0 EMF. You all know what I'm talking about, right? At this instance here, if the magnet is north and south, you think about it lah, right? North and south, the magnetic field is going down like this, right? Bloody hell, if the coil at this instance is moving in this direction, because their mind, they fixated that, oh, when the coil is like this, it's maximum. When the coil is like this, then it's minimum. Don't think like that, guys. It will do you no good. You need to know that it is the movement of the coil against the magnetic field that is generating the maximum and the minimum. I repeat, it is the movement of the coil against the magnetic field that is generating the maximum and the minimum. You better read the question before you know, base your understanding on memory. Thanks, GG. Okay. Everybody, good. If you have no questions, oh look, we have one question at the bottom here. Please attempt the first question. You have exactly 5 minutes to attempt it. Then we will discuss the answers. All the answers should be no. Unhealthy food. But so language. The trial, haven't study purpose talking about. Cái là họ nó sẽ phải lo về một có ba cancer. Why everyone here
Ministers, he decided to review. Without looking correctly. Okay. What I want to do again. You should come. Oh, shit. Oh. Sorry, Raj, as usual. But good. Let's go through the questions together, real quick. Okay. No problem. Okay. A look at this question here, boys and girls. What do they want from you? A student turns the handle of an alternating current generator and the coil rotates, obviously. And then figure 8.1 shows the structure of the AC generator. There's the coil, there's the handle, there's the coil again, slip ring, and voltage output here. The voltage output is usually where you connect to your whatever electrical device, for those who do not know. Right. Anyways. And there is an alternating voltage output between the two terminals. Explain why, once again, why rotating the coil produces an output voltage this is essentially once again electromagnetic induction, right? Which is, oh my god, 3 marks once again. So what do? You say as the handle is spun, right? Or you say as you spin the handle, whatever way, the coils here will actually cut through the magnetic field, right? And when the magnetic field is cut, it will generate an EMF, which will ultimately induce a current, as you can see here. Look at this once again. The magnetic field is basically cut, which will generate EMF, and bam, you get your 3 marks again. Right, so it's always boiling down to electromagnetic induction, guys. It's always boiling back down into a electromagnetic induction. Good, Raj. You got the first one correct. Okay. You can write anything. I think by now you should be able to write this down. It's literally just the electromagnetic induction topic once again. Boy, why is there only one sentence, bro? There's 3 lines. You don't know what to write, man. So you die. Okay, you mentioned these 3 things, and it's good to go already. Literally construct your own sentence. We've written this down 1,000 times by now. And one more thing I want to teach you guys, don't be too fixated with the points. As you can see here, magnetic field mentioned, they already give you 1 mark. Then the second mark, the wires will cut through the magnetic field. So it's essentially the same thing, right? Which a lot of students, they always ask me, hey, teacher, this one can get 3 marks. Hey, teacher, this one can get 2 marks. The real answer is, I don't know. Sometimes the mark scheme is very funny. The concept is more important. Right now, what you know is better than just trying to fixate on the marks here. Okay. Okay. Then the next part here, what do they want? State the position of the coil when the alternating output is at maximum value and explain why the maximum output occurs here. So looking at this right now, will this be maximum or minimum? Why? Good. You're going to say, at this instance here, you could say, you could either describe these 2 ways. When the coil is at the horizontal position, it will generate the maximum voltage because at this instance here, the coil cuts through the magnetic field line perpendicularly. Okay, so you can write anything along the lines, right? You could say something like, when coil is at horizontal position, maximum value occurs because completes half a rotation.
Raj, I think your answer is wrong for the second one. What do you mean half a rotation? At this current position, it generates the maximum meridian. Right. Half a rotation is vertical. If it goes half a rotation, if it goes half a rotation, it will be exactly this exact same position here. Are you trying to talk about 90 degrees, where the coil is like this position here? Is that what you're trying to say? But at this 1/4 of it, it will actually give you the minimum. Because at this instance here, it will move parallel with the magnetic field already at this point. Do you see it or not? At this instance here, where the coil is like horizontal, it is at maximum meridian. So you just say at this exact instance here, when the coil is horizontal. Do you know what I'm talking about? Okay, everyone. Let's do another question. Oh, what? There's no other question. Yeah. Early dismissal today. Yeah, I'm going to teach you the basis first for the next chapter. We're not going to be able to finish this next topic, but let me teach you the basis first. You know how we always talked about Fleming's left-hand rule? Fleming's left-hand rule is like, okay, there must be a magnetic field, and then there must also be what again? What must be provided for Fleming's left-hand rule? The current, right? There must be a current generated, right? If let's say today the current is going into the paper, will this thing be forced up or forced down? Up. Wait, I want to ask you first, left hand or right hand? What? Which hand first? Left or right? It's supposed to be the left. Hand. So, will it go up or down? In. Up. Do you say up? Why up? Bloody hell, what does the X mean? It's not into you, it's into the screen, bro. It's into the screen. Oi, bloody hell! You're supposed to have like to the left or right, to the right here, north to south. Then the current is going into the screen, not in towards you. And then you'll have your force finger downwards, right? By right, your force finger should be going down here, right? Do you know that actually Fleming's did not just one day drank a lot of alcohol or some cocaine or whatever and decided to use these two hands? He actually observed one thing which is very important. It is actually the interaction between the magnetic field line between each and every one of them. Do you know what is actually happening here? The real thing that is actually happening here is that number one, when there is current running through a conductor, it will have its own what again? If there is current running through a conductor, what will it generate? No, before that, not EMF. What would happen if I have current flowing in the conductor? What will it generate? What's the thing called? What's the thing called? It's magnetic field, are you fools? You remember or not? I just told you this 2 weeks ago. I haven't opened the X and the dot story on Sunday for you guys. Remember or not, the X and the dot, it will generate its own magnetic field, right? So it will generate a magnetic field like this. How do I determine the direction of the magnetic field again? What's the hand called? It's called the right hand grip rule, bro.
From here, I point into the screen and I notice that my 4 fingers are rotating in the clockwise direction, right? So first and foremost, this thing here is the magnetic field generated by the current, right? And then, guys, what happens here is this magnet has its own magnetic field, right? The magnetic field always goes from north to south, right? But in this instance here, there's something in between, So what this is what I like to call the follow the roundabout rule. You know, like if you're coming from one intersection and then there's a roundabout like this, you sure as hell wouldn't drive in this direction, right? Unless you want an appointment with the devil lah, right? If not, for sure, you're going to roll in this direction, right? This is the magnetic field from the permanent magnet. Magnetic field from the permanent magnet here. Okay, and then from here, once you have this understanding, right? You all played with guitars before, right? Maybe some of you you have no musical talent, it's fine, but you've definitely seen someone pluck a guitar before, right? No, get out of your cave more then. Right, if you see someone pluck a guitar, usually the strings, when they're plucked up, it kind of resembles this scenario here, right? It kind of resembles it. When you let go of the string, what's going to happen? It will shoot downwards, right? It will shoot downwards, right? This is exactly what's happening here also. This is the reason why there is a force that generates it downwards here. It's because, I repeat this, it's because it's the interaction between the magnet from the, the magnetic field from the current and the magnetic field from the permanent magnet. He did not just one day drink a lot of alcohol, smoke some weed, and like snort some cocaine, and then like, oh, this looks kind of funny, and then bam, I impose this rule onto everyone below. No, he actually observed the interaction between the magnetic fields, and he found out that, oh, because of this, I can use Fleming's left-hand rule to show that, hey, actually it makes sense, and it will be the same for the other situation also. If let's say, for example, today I got a different situation, north and south here. And now I've got like current dot here. Current dot means to say the magnetic field is going to go anti-clockwise, right? Right. And then this magnetic field is going to once again follow the roundabout, right? Without using the Fleming's left-hand rule, I know for a fact that the force generated will be in this direction because it is to follow the roundabout and the guitar string rule here. You understand or not? Right. Yeah. Hold this concept, guys. We're gonna use this concept for the next class. Next class, we're gonna finish up with the DC. Then after that, we're gonna finish up with transformer, and we'll be done with the whole electricity chapter. Then we'll be done. Once after that, we have two more main topics, and we're done with the syllabus already. I'm gonna try to rush it faster because some of you guys are having exam in major that I want to cover some past year papers with you guys. Okay. All right, that's going to be it for today, guys. I'll see you all next week.
So yung tadi ya,